Automating banking workflows with Python. This lesson will teach you how to use Python to automate repetitive banking tasks. Automation is important in banking because it improves efficiency, reduces errors, and allows staff to focus on high-value work. You will learn to organize transaction data, detect suspicious activity, and streamline operations using common Python patterns. By the end, you will be able to build simple automation scripts and understand how banks use automation daily. Running the cell now. First, let us import our main tools for data handling and computation. We import pandas to manage and analyze tabular data. We import NumPy for fast numeric operations when generating synthetic data. We import warnings to help suppress unnecessary warning messages. We ignore all warnings to reduce output noise and keep workflows clear. Running the cell now. Now try writing a line to import matplotlib or seaborn yourself to see how plotting imports work. Remember to always set warnings filters where needed. Understanding the data for banking automation. Each dataset in banking represents different aspects, such as transactions, customers, or account types. Data tables are usually structured with rows as records and columns as fields or features. Beginners often make mistakes like using the wrong column as the unique identifier, forgetting to check for duplicates, or mixing up data types such as dates and strings. Carefully explore your datasets before building automations to avoid costly mistakes later. Running the cell now. Let us create a synthetic banking transactions dataset to practice automating workflows. We set the random C to 42 so our results are reproducible. We decide to work with 1,000 transactions. We plan to have 200 unique customers in our dataset. We begin building a pandas data frame for our transactions. We generate unique transaction identifiers sequentially. We randomly assign each transaction to a customer. We create realistic transaction amounts using a normal distribution and rounding. We assign each transaction as either a debit or credit. We randomly choose the channel for each transaction, like ATM or online. We generate a unique date and time for each transaction, 1 hour apart. We finish the transaction table creation. We print the shape of the resulting data frame. We display the first 3 records to preview our synthetic data. Running the cell now. This output shows the initial overview of our synthetic banking transactions dataset, with 1,000 rows and 6 columns representing key features like IDs, amounts, types, channels, and timestamps. Notice how transaction_ID is a unique sequential identifier, which is crucial to avoid ID duplication mistakes, while customer_ID repeats across transactions, linking multiple records to the same customer. This step confirms that the data is structured correctly before moving on to analysis or automation. Practice, change the number of transactions to 500 and see how the output changes. Let us set up a synthetic customers table to enrich our workflow. We create a list of 200 customer identity codes. We start building a new data frame for our customers. We populate the table with unique customer identifiers. We assign the first 150 as retail customers, the rest as business customers. We assign the first 100 to metro and next 100 to regional regions. We finish our customers table. We print the shape of the table to verify dimensions. We preview the first 3 customer entries. Running the cell now. This output shows the customer's dataset with 200 rows and 3 columns, confirming the expected size. Key fields include a unique customer_ID in a consistent format, a segment mostly retail with some business customers, and 2 regions evenly split. Checking the shape and sample rows helps ensure data correctness before automation steps. Try adding a new segment category called VIP to the customer table as a challenge. Now let us create a synthetic accounts table for workflow examples that connect customers and transactions. We set the random C to 42 for reproducibility. We build a data frame to hold account details. We make unique account identifiers for 200 accounts. We assign each account to a customer. We randomly pick each account as savings, check, or credit. We generate an open date for every account spaced 30 days apart. We finish setting up the accounts table. We print the size or shape of the newly created table. We preview the first 3 rows for quick inspection. Running the cell now. The output shows a data frame with 200 rows and 4 columns, confirming the expected dataset size for bank accounts. Key columns like account_ID serve as unique identifiers, while customer_ID links each account to a customer, and open_date is a properly formatted date type. This initial exploration reassures us that the data structure matches our intent and is ready for further analysis without duplication or data type errors. Try experimenting by changing the account types or adding a closed_date column. Beginner example 1, filter high-value transactions. Learn to select transactions above a certain value. Filtering is a simple automation that supports fraud detection and reporting. Running the cell now. Let us automate retrieval of high-value transactions, such as those above 250. Here we filter the data frame for rows with amounts over 250. We preview the first 3 results to check the filter. We count the total number of high-value transactions found. Running the cell now. This output shows the first 3 transactions where the amount is greater than $250, illustrating how filtering helps isolate high-value activities. Notice the key columns like amount, transaction_type, and channel, which provide context for these significant transactions. The total count of 54 confirms how many such transactions meet this criteria, demonstrating a simple way to flag potentially important or suspicious cases for further review. Practice, try changing the threshold to 300 and see how many are left. Beginner example 2, select online transactions. Isolate transactions performed through the online channel. This helps business teams analyze digital banking trends. Running the cell now. Let us extract all transactions made through online banking for digital usage analysis. We filter our data frame to select only online transaction rows. We preview 3 rows to confirm our code works as expected. We print the total count of online transactions. Running the cell now. Here, we filtered the dataset to include only transactions made through the online channel, as shown by the channel column in the output. Notice the preview displays the first 3 online transactions along with key details like amount and transaction type, and the total count of 236 online transactions highlights the volume of digital activity. This step is crucial for focusing analysis specifically on online banking trends. Try finding the share of online transactions by dividing by the total transaction count. Beginner example 3, count transactions per customer. Count total transactions for each customer. Summarizing by customer supports personalized offers or flagging inactive accounts. Running the cell now. Let us automate the counting of transactions for every customer. We group the data frame by customer identity and count how many transactions each has. We preview the first 3 customer counts. Running the cell now. Here, we see the first 3 rows of our summarized data showing each customer's total transaction count. Notice how each customer_ID is paired with a TXN_count that tells us how many transactions they made, which helps identify active customers or tailor offers. This output confirms the grouping and counting worked as intended to support customer-level insights. See if you can sort the output to show the most active customers at the top. Intermediate example 1, merge transactions and customer data. Enrich transaction logs with customer segment and region information. Merging datasets is a key banking automation for reporting or compliance. Running the cell now. Let us merge transaction data with customer information for holistic reporting. We perform a left join between transactions and customers using customer identity. We preview the merged result for the first 3 rows. Running the cell now. Here we see the first 3 rows of the merged dataset, where each transaction is now enriched with the customer's segment and region information. Notice how the segment and region columns come from the customer data, added by the left join on customer_ID, allowing for more detailed analysis and reporting in banking automation. This merge enables combining transactional and customer insights for compliance or targeted decision-making. Try merging transactions with account data for deeper analysis. Intermediate example 2, flag suspicious large debits. Automate the detection of large debit transactions for monitoring fraud risks. This enables proactive alerts and compliance. Running the cell now. Let us set up an automation to flag high-value debits which may be suspicious. We use NumPy to add a flag whenever a debit over 400 occurs. We show transaction details and flag status for the first 5 rows. We count and display the number of detected suspicious transactions. Running the cell now. In this output, the suspicious_flag column marks transactions over $400 that are debits, but none of the first 5 rows meet this criteria, all showing a flag of 0. The printed total of 0 suspicious transactions indicates no large debit transactions were detected in this sample, demonstrating the code's intent to automatically identify potential fraud risks by flagging high-value debits. Practice, adjust the threshold and try flagging only online channel debits. Intermediate example 3, automate daily transaction summary. Automate daily summary reports by aggregating transaction amounts and counts by day. Daily reporting reduces manual work and errors. Running the cell now. Let us automate a daily report showing total volume and number of transactions. We add a new column containing only the date for easier grouping. We aggregate transaction amounts and counts for each day. We rename the output columns for clarity. We preview the first 3 days of our daily summary. Running the cell now. This output shows a daily summary of transaction amounts and counts, with each row representing a specific date. Notice the consistent transaction count of 24 per day, while the total amounts vary, highlighting daily fluctuations in transaction volume. This aggregation automates reporting by quickly summarizing key metrics, reducing manual effort and potential errors. Practice, try grouping by channel as well as date for multidimensional summaries. Advanced example 1, batch export suspicious transactions. Automate exporting a CSV of flagged suspicious transactions for compliance reviews. Exporting is a key part of workflow automation in banking. Running the cell now. Let us create and save a file listing all suspicious transactions for further review. We select only transactions flagged as suspicious. We export these records to a CSV file for subsequent sharing or audit. Running the cell now. Now opening the suspicious transaction CSV so you can review the flagged records. Try opening the exported CSV file to review its structure. Advanced example 2, automate report distribution via email, simulated. Although we will not send real emails, automating report saving prepares data for downstream tasks. In real banking workflows, you often automate emailing reports to compliance officers. Running the cell now. As a simulation for report distribution, let us create a simple indicator file. We comment that real emailing is out of scope in this example, but we simulate by saving a simple file. We open a file called report_ready.txt for writing. We write a message saying the compliance report is ready. Running the cell now. Now opening the report indicator file to verify the reporting automation result. Check that the report_ready.txt file exists as confirmation of a completed automation step. Advanced example 3, automate inactive account detection. Find customers who have not transacted in the last 6 months. This automation helps banks comply with regulations and reduce dormant account risk. Running the cell now. Let us automate checking for inactive customers over the past 6 months. We find the most recent transaction date in our data. We calculate the date that is 180 days before the latest. We collect all customer identities active after this threshold. We gather all customer identities from our records. We subtract active from all to find customers without recent activity. We print the total number of inactive customers detected. Running the cell now. This output shows that there are 2 customers who haven't made any transactions in the last 6 months. The code calculates this by comparing transaction dates against a cutoff date and subtracting active customers from the full customer list. This helps automate identifying dormant accounts, crucial for regulatory compliance and risk management. Practice: print some of the inactive customer IDs for review. Error handling and debugging in automation. Always check for missing data and unexpected values to avoid automation failures. Use try, except, and assert statements for safe automated pipelines. Running the cell now. Let us write a quick check to ensure our automation does not break due to missing data. We use a try block to assert there are no missing values in the amount column. We run the assertion and print a confirmation if all values are present. We print a success message if there are no missing values. If an assertion error occurs, we catch it and print a warning. This approach helps us fail gracefully and catch problems early. Running the cell now. This output confirms that the amount column in the dataset contains no missing values, which is essential for preventing errors in automated workflows. The try except with assert statement effectively checks data integrity before proceeding, highlighting a key technique in error handling to ensure smooth automation. You can try deliberately introducing a missing value and rerun this block to test error detection. Best practices and common patterns. Always set random seeds in workflows that generate data. Automate data checks to catch issues before reports are generated. Modularize your code into small functions for automation reusability. Clean all data inputs before analysis or export. Running the cell now. Let us write a reusable function to automate cleaning of incoming transaction data. We define a function to clean transaction records. We copy the data to avoid altering the original. We filter out transactions with non-positive amounts. We remove transactions that are implausibly large to avoid outliers. We return the cleaned data frame. We use the cleaning function on our sample data. We compare the size before and after cleaning. Running the cell now. This output shows that cleaning the transaction data removed 7 rows with amounts outside the valid range, less than or equal to 0 or greater than or equal to 10,000, highlighting the importance of input data validation. Notice how the small loss in row count preserves data quality without drastically reducing dataset size, reinforcing the practice of cleaning all inputs before further analysis. Practice: add more rules to this cleaning function as needed for your use case. End-to-end mini-banking workflow automation. Let us combine what we have learned by detecting, flagging, and exporting suspicious transactions from raw data. Running the cell now. Let us put together cleaning, flagging, and export automation steps in a single block. We set the random seed to 42 for reproducibility. We clean the data to remove outliers and bad records. We flag suspicious debit transactions with amounts over 400. We export these records to a CSV file as our workflow result. We print confirmation that the workflow finished successfully. Running the cell now. This output confirms that the workflow successfully identified and exported suspicious debit transactions over $400 from the clean dataset. Notice how the code filters transactions by amount and type to target potentially risky activities, aligning with our goal to automate detection and reporting in the banking workflow. Let us open the final exported workflow file so you can review the automation output. Try editing the export file name or filtering on different rules to practice customizing your automation. Subscribe to YouTube for more workflow automation tutorials. Great work completing the automation lesson. Practice by applying these steps to your own datasets. For step-by-step videos, search for Banking Data Automation Python on YouTube. You are now ready to tackle real-world banking automation scenarios. Running the cell now.